right, circular functions. Called circular function, sine cos tan, because it is related to the circle. Now, the first thing is, let's have a think about the rule. When we're working with circles, back in year H, you had the formula for a circumference, pi times diameter, or you could also have C is equal to, oh my god, so you got pi d, pi times d, and 2 pi r, because diameter is twice the radius, right? So 2 times pi times the radius, that is also giving you the circumference. Now, logically, in a unit circle, this is called a unit circle. We're saying unit meaning that, what if I just took a length of 1? Now, that could be 1 centimeter, could be 1 millimeter, it's just a unit, right? If it's a unit of 1, that means it's 1 up here, 1 down here, 1 across, and 1 across as well. But that also tells me that the radius must be 1. If that is true, well then, according to the circumference of this unit circle, it would then be 2 times pi times the radius, which is 1. Hence why we know that the distance of a unit circle is 2 pi. Now with that ratio, this is what the first exercise is to learn the conversion between degrees and radians, or at least the understanding. We know so far that in a full circle, a full revolution, the angle is 360 degrees, okay? It's an arbitrary number, but it's a really nice number. If you search it up, why we chose 360, it's because there's a lot of factors that can be used from it compared to any other number that you can come up with. Okay, so 360 is one of the nice numbers that we chose. I mean, it could have been 100 for that sake, but then it means every other calculation would be much harder. So we go with 360. So one revolution is 360, but we also know that means the distance around the unit circle, which is what the radians measure, measures the distance around. So when you say 1 radian, you're doing a portion on the outside distance. That's what you're doing. So we know that 360 degrees is equivalent to 2 pi distance, because the angle versus the ratio of the circle around the distance around the circle. So if 360 is equal to 2 pi, then if I divide both sides by 2, I also get 180 equals 2 pi, which means that when you do half a circle, that's pi distance, which is why last year you've learnt 0 going anti-clockwise up to this point over here, that is pi, and all the way back here, that's 2 pi, right? That's why you have to learn to put in the points in radian, and then obviously a quarter of 2 pi would then be pi on 2, and then this is 3 pi on 2, right? So I've got my circle. Now, the conversion that they gave to you, which I've given to you here already, is if I know that 360 is equal to 2 pi, well, if I want to find out, well, what is 1 degree equivalent to, all I had to do is I had to say just divide 360 by 360. That will give me 1 degree. But then if I divide one side by 360 and divide the other side by 360, that now gives me 2 pi on 360, which nicely simplifies 2 pi on 180. And that's one of the first rules that you have in exercise 6A. Simply, if I had 30 degrees and I said, what is 30 degrees converted to radians? Well, clearly 1 to 30, I'd have to times this by 30. But then that means I'll times this side by 30. And that was the rule that you had from last year. Yeah, so if you took the degrees times by pi on 180, that changes it to radians, which is why it works out to be pi on 6, because 30 and 180 simplifies. The notes, spare sheets are up the front if you need some extras. And then same thing, if you wanted to do radians 2 degrees, same idea. I want 1 radian, not 2 pi radians. So then I'll do the same thing. I say divide both sides by 2 pi. And you can see 2 pi divided by 2 pi gives me 1 radian, which remember, that's the distance around the circle. It's the circumference. So that one portion, 1 radian distance, is equivalent to 360 divided by 2 pi, which ends up being 180 on pi. So if you had any radians, say 5 radian, and you wanted to convert to degrees, well then 5 radians is 5 times that amount. So then you times 5 to this side. And that's exercise 6A. Last year you would have done the same thing in the first exercise to convert radians to degrees, degrees to radians, and it all comes from just the basic fact that 360 degrees is proportional to the circumference of a unit circle, which is 2 pi. That's where it is. So far, so good? Okay, so that's exercise 6A, just knowing how to convert the degrees to radians, and it's important depending on the question. If the question gives you a trigonometric function, sometimes they give it to you in degrees, but then your calculator is in radian mode. So you just got to be careful when you enter in the x values. Is it degree mode or is it radian mode? However, the conversion can help. You can change the formula from a degree to a radian function. That's the idea. Okay? Let's do some examples. Not examples, sorry. Moving on to the idea that we know a unit circle has 2 pi circumference. Then you learnt last year that in a unit circle, which I'll go back to the picture again, if I have a radius of 1, remember we're looking at the points on the circle. This is the circle, and every point has an x and a y coordinate. What was the x representative of again from last year? What'd you say? Cos. X is the cos, and if you're wondering why, well, that little point there on your circle can create a nice right-angled triangle. And the only things that you learnt about right-angled triangles is either Pythagoras' theorem or trigonometric ratios. And we know that this angle that I've created makes this side, which is the y values, that's the opposite side. And this length, this x length, this is the x length, and then obviously this is your y height. The y values are related to the opposite length, and then the x length is related to the adjacent. And so that's why if you think about why is x related to cos, because cos of the angle is adjacent over hypotenuse. So if I wrote it down, adjacent, whatever that x length is, which is x, divided by hypotenuse, which is 1, and it turns out x is equal to cos of theta. Which is why, if you do the same thing for y values is actually the opposite over hypotenuse, so hence sine of this angle gives you the y values. So sine of an angle will tell you the y-axis values. Okay, that's where it's coming from. So it's pretty much working with your triangle, that this length, this height, is equivalent to sine of the angle. This length is equivalent to cos of the angle. Okay, so fill in the points. Let's fill in the notes. X is equivalent to cos of the angle, and the y coordinate is equivalent to sine of that same angle. The x and y can be rewritten as cos theta, sine theta. Cool. Therefore, looking at the unit circle, let's find sine of 180 degrees. So if you think about it, let's draw a unit circle just so you can visualize here. Here's a circle. Here's my axes. 0 starts at this point. We always go anti-clockwise. So if I say, what is sine of 180 degrees? What I'm saying is, what is the y value? What's the y coordinate after I have rotated 180 degrees? So starting from here, I'm going to go 180. So I turn all the way 180 and then I stop. This is the point where I'm at. So this is the point now. So I've gone from 0 all the way 180 degrees because that's 180 degrees there. And I've stopped right here. What they're asking when they say sine of 180 is they're saying, at that point you've got an x and y coordinate. What is the y value at that point? Now there's a couple of things we already know about a unit circle. We know that the radius was 1. So that means from here to here is 1. Up here the y value is 1. Down here the y value is -1. And then across here that that x value is -1 there. So if I ask you, what is the coordinate exactly at this point? Well, that's at x equals to -1, and y must be 0. So hence why, just looking at the unit circle as you can picture it, we can then say the y value must be 0. So this is when x is -1 and y is 0. So had I asked you the other question, if I said, what is cos of 180? You would have told me it's -1. Because you're just really asking, what's the x coordinate when the degrees is 180? Okay, so it's all about working around the circle. And hopefully you can quickly pick up why we work in radians and not degrees. Because if I asked you now, what is sine of, 2080 degrees? So the problem is that if I asked you, where is 2080 degrees? We don't know where we are in the circle. We know that going all the way around is 360 there. If I went 10 times, 3,600 is here. But where's 2080? That makes it harder to visualize where I am on the circle. Whereas radians, it's nice because instead of 0 to 180 degrees to 360, it's so much easier to work with 0, pi, 2 pi, 3 pi, 4 pi. Because the pi, all the evens end up here, all the odds end up here. So if I change that to radians, it's much easier to figure out roughly where I'm going to be at. I can estimate. That's why we work in radians instead of degrees. Okay? All right, let's do the same thing. Let's test your understanding now. What is cos of 270 degrees? Let's go with Ryan. 0. That is correct. Again, we can see 270 degrees is right here. And right at that point, x coordinate is 0, y is -1. What is C, tan of 270 degrees? Let's go with Lockie. Oh, Rango. It is undefined. 270 degrees is the same spot here. And remember, tan is finding the gradient. Clearly, that's a vertical line, so gradient is undefined. If you weren't sure with that, you could also test sine theta over cos theta. That's the property of a tan. And you can see sine is -1, but cos is 0. You can't divide -1 by 0. Okay, so it's undefined. Now let's work in radians. Cos of 2 pi. What is cos of 2 pi? Can I please have, let's go with Tara. What's cos of 2 pi? 1. Very good. Okay, so we can see 2 pi is right there. And right at that length, x is 1, y is 0. Okay? Now, there is a table over here. Can I get a show of hands who have memorized the exact values table? 2, 3, 4. Okay. You must know this, like your times tables. Now, there's 2 ways to do it. On the next page, I show you my way that I've taught to other students. But the other way that you might have seen already is your equilateral triangle and then your isosceles triangle. Right? So you've got 90 degrees there, then isosceles. If that's 90, this must be 45. 45, length of 1, using Pythagoras' theorem. 1 squared plus 1 squared, that's √2. Now, you can work out sine of 45, cos of 45, and then tan 45 as well. The other one, if you use these circles, equilateral triangle, they're all 60, 60, 60. Cut that in half, 30, 30, 90 degrees, 90 degrees. And again, same thing, you can work out the length. If that was 2, then it's 1, 1. And then you can work out that height from the same idea. Okay? Now, the one I like is this one. Let's use your hands. Hands up if you've seen the hand method before. Oh, you got 1, 2, 3. Oh, a few of you have. This one's meant to be my special one, but let's just see how many of you have learned it already. So the hand method, for those who, again, if you can't memorize the equilateral triangle and then the isosceles triangle to figure out the exact values, this is the other way. So hand method, your 5 fingers represent, so from left to right, represents the smallest angle you have in radians all the way to the largest angle you can have. So if you're not used to radians yet, you can write on the side. So usually I get my students to write on their hand to start off with. In year 11, year 12, I'm going to assume you guys know it already. So 0, 30 degrees, 45, 60, 90. Those are your 5 special angles, right? And that comes from the property we just talked about just now. Now these are your 5 special angles. Here's the formula inside your palm. Root of something divided by 2. How does it work? Very easy. If I wanted you to find sine of pi and 3, first thing is you need to know what pi and 3 is, and notice the numbers, denominators decrease. 6, 4, 3, that's 60 degrees. So it is your ring finger. Drop down the ring finger. So if I drop this finger down, I'm just going to cross it off. There you go. Imagine you drop that one down. If you're looking for sine, notice I wrote sine is on the left side and cos is on the, sorry, what's that? Yeah, left, right. Cos is on the right side. You count the number of fingers you see. So for sine, sine is on the left side of wherever the finger you've dropped down. So if I count the number of fingers on the left, how many fingers do I have? 3. So on the left, so we got 1, 2, 3 there. Yeah, so 3 fingers. I would then say the answer is square root of 3 fingers divided by 2. And that gives you sine of 60. So sine of 60 must be root 3 on 2. If you wanted to try it with cos of pi on 2, same thing. Pi on 2 is 90 degrees there, so that's my pinky. Drop down the pinky. And then the question is, how many fingers do I have for cos? Cos is on the right side of that finger. Now, do I have any fingers on the right side of it? No. So then it would be root of 0 divided by 2, which ends up being 0. So cos of pi on 2 is 0. Now, you'll find that just using this formula and the fingers I just showed you, you would now know 10 out of the 15 exact values, just simply following your fingers. Let's do a bit of a test. Let's try out, I'm going to call out a couple of students now so you can try out the finger method. What is cos of 60 degrees? Can I please have, let's go with Albert. What's cos of 60 degrees? Dropping 60 down, so this is my ring finger down.
Yeah, so it's 1 over 2. 1 over 2, that's 1 over 2.
Very good. And that's the answer. So how many fingers do I have on the right side? Once I drop the 60-degree finger down, I've got 1. So root of 1, then divided by 2. So root of 1 is 1. 1 over 2 is half. Right? So yes, that equals to half. Let's try another one. Noah, sine of 30 degrees. What does that give me?
30 degrees, root 3 on 2.
That would have been correct if it was sine on that side, but sine is on the left.
So it'd be 1 on root 2.
The finger, square root first, and then divide by 2. So how many fingers do you have?
3. Oh, I'm so confused.
Now let's do this. So which one's my 30-degree finger? Because I want to find sine of 30. Right?
The root on pi on 6.
Good. So I drop this one down.
Yeah.
Now, sine is the number of fingers you have on the left side of that. So I only got 1.
Yeah.
So the formula says you're going to square root the number of fingers first.
1 on 2.
1 on 2. Very good. So root of the number of fingers first. So root of 1 and then divided by 2. So it is 1 on 2. Very good. Let's try another one. Samuel. Let's try sine of 45 degrees.
That would be root 2 on 2.
Yeah, root 2 on 2. Alternatively, sometimes your textbook would say it's 1 on root 2. They're just rationalized denominator. Okay, so times the bottom and top by root 2. That's how you get root 2 and 2, but they're both the same, equivalent. Okay, let's try another one. What is sine of 90 degrees? Can I please have, let's go with Adrian. That's, yes, you're right. That's right. So there are 4 fingers on your side. So if you drop the pinky, which is 90 degrees, there are 4 fingers. Square root the 4, which gives you 2, and then divide that by 2 gives you 1. So sine of 90 is equal to 1. Okay, so if we look at the exact values again, you see everything to do with sine and cos, you technically can tick off all of this, which is the one formula I just gave you. Okay, so with the fingers, everything, all the 5 special angles, you will remember all 10. Okay? Now, how do you remember the last one? This one I didn't find on YouTube, so this one I made up, and I haven't seen anyone write it down, so this is how I do tan, just using the properties. Since tan is sine over cos, then I realized all you had to do was that you still drop down the fingers just the way you do. Number of the angles are still all the same. The formula is just slightly different. Instead of root the number of fingers, it's root of, you got to do sine divided by cos first. Okay, so here's an example. If I wanted to do tan of 60 degrees, here we go. Which one's my 60-degree finger? Ring. So I drop down my ring. So remember, sine is the number of fingers on the left, cos is the number of fingers on the right. So right now, number of sine fingers I have on the left is 3, divided by number of cos fingers, which I have 1, and then square root that. So 3 over 1 is 3, and then therefore the answer must be root 3. Does that make sense? So there's just a slight change in the formula, but then that allows you to remember the last 5. So let's do another one. Tan of pi on 6. Let's go, Mia. Let's have a go. Tan of pi on 6. Root 1 on Sorry, which? On 3, yes. So you got root of number of sine fingers, I've got 1. Number of cos fingers, I've got 3. And conveniently, we do know what root of 1 is. Root of 1 is just 1. Root of 3, I don't know. So the answer must be 1 on root 3. Let's try another one. Can I pick? Ian, what is tan of... Which one haven't I done yet? Oh, pi on 4. Tan of pi on 4. Use the finger method. So pi on 4 is my middle finger. It goes down. Not sure. Let's go with Neil. Tan of pi on 4. 1. And how do we get 1? Same thing again. Drop down your middle finger. Count the number of sine fingers I have. It's 2 divided by 2. So 2 sine versus 2 cos. Square root it. Root of 1 is 1. So with the 2 formulas that I've got so far, then you got your 2 formulas that allows you to memorize your exact values. Now that is exercise 6B. One of the challenges from last year, thanks team. One of the challenges from last year that year 11 struggle with is because they don't know the exact values, then when we do symmetry properties, that is the basics to solving a trigonometric ratio or equation. You can't solve equations without knowing symmetry properties, and you can't really know your symmetry properties correctly without knowing your exact values. So it's like your times tables. If you don't know your times tables, you can't do fractions. You can't do fractions, and you can't do percentages. Yeah, it's the same idea. So this is one of the first steps that you must learn. You must memorize that. You must have some form. You either use the triangles or you use the hand method I just showed. Regardless, I want you, by the end of next week, which I'll be testing you along the way, I'll be calling out your name, and you should be able to answer me. You should be able to do something like, if I said, what is sine of 2 pi on 3? You're using not only exact values and symmetry properties in your head, and you can tell me the answer. Out of curiosity, who knows what sine of 2 pi on 3 is at the moment? What was that? Root 3 on 2. Okay, and again, how I'm picturing it in my head, which is what I'm trying to train you to do, is this is your unit circle. 2 pi on 3 is almost 3 pi on 3. Right? It's just short of pi by pi on 3. So all I'm picturing is pi is over here, short of that, so I must be in this region. I don't really care what the angle is. All I care about is the region. At this point, if I asked you sine is the y value. So I know the y value is clearly going to be a positive. But the angle, I was short by pi on 3. So all I had to figure out was, what is sine of pi on 3? That's literally like you saying, what is sine of pi on 3 there? You know the answer is going to be positive because it's in that region. Sine of pi on 3, use your fingers or the triangles. So pi on 3 is this finger. Got 3 fingers here. So root of 3 on 2. That ability to just do what I just said there, where I ask you what is sine of 2 pi on 3, you have to be able to do that the way I just asked at this point. At year 11 level, I'm still training them. I'll train them in term 3. But at year 12 level, you need to be at the point where I'll just ask you and you know. So I should be asking things like, cos of 22 pi on 6. Tell me that. Wait, does that work? No. Yeah, you could do that, but that's a bit harder. Let's do 23 pi on 6. Okay? If I asked you what is cos, let's write that down. Cos of 23 pi on 6. You have to try to work that in your head. Okay, and then tell me the value. That is training your exact values and your symmetry properties, which is what 6B and 6C is. Okay? Now, for those who are finding this part that I just described from last year tricky, that's what the next examples are for. Okay? For those who know it already, fantastic. You just need to work on speed and accuracy. For those who don't know this, that's what we're doing next. Okay? So here we go. Actually, out of curiosity, anyone know? Root 3 on 2. Let's have a think. Unit circle, 23 on 6. To me, that's closest to it is 24 on 6, which is 4 pi. 4 pi is here. So I'm short of 4 pi by 1 pi on 4 pi on 6. Okay, I'm just missing that pi on 6. So that means I must be down here. So just before 4 pi, I must have gone all the way around, and eventually I ended up at this spot here. All I care about is the region. That region there, cos, is your x values, and clearly cos is positive. So all I have to figure out is, well, I'm missing pi on 6. So I'm really just working out cos of pi on 6. Go through your fingers. Pi on 6 is your 30-degree finger. Drop it down. Cos, I've got 3 fingers. So it's root of 3 on 2. And it's positive. Yeah, cos is still positive. Yeah, so it's positive. Because that's like that x value there is still positive. Yeah. If it was sine, then it would have been negative. Yeah. Okay, so that ability to go through what I just described, that's what you're trying to picture, the unit circle. All right? All right, team, let's do some examples to get you going. Let's practice. Here we go. So all of these ones, this is symmetry property. Now I flip to this page. So those who struggled with symmetry properties from last year, this is going to be your part of the lesson to understand now, okay? Here we go. Because after this part of the session, you're going to have to train in your own time to be able to do these ones in your head, okay? So today's lesson, I'm going to guide you down, but then eventually you have to be able to do that speed-wise, yeah? So here we go. Here's your unit circle. I'm starting off pretty easy. I say cos of pi on 3. Let's draw that picture. Pi on 3 as a degree, what is that again? 60. So what you should be picturing is 60 degrees is maybe about there. That's 60. I've got this point. That's x, that's y. That creates a nice triangle for me. That triangle is made up of a y value that is positive. That's the height. And then an x value that tells you the length of that triangle. Okay? Cos will tell you the length. Sine will tell you the height of that triangle. Yeah? So when I say cos of pi on 3, this is why you have to remember your exact values. Cos of pi on 3 is equal to 1 on 2. Very good. So again, for those who can't remember, using your hand, pi on 3 is your ring finger. Drop it down. Cos is the number of fingers on the right of that side. I've got 1 finger. So square root of 1, which is 1, and then divide that by 2. That was the formula I gave. Yeah? So root of the number of fingers, divide that by 2, I got half. What does that mean? Cos is your x value. So I'm telling you that this length here is half. I haven't worked out sine. I don't care about sine at the moment. Yeah? I'm interested in just cos. Symmetry properties is about using that one triangle we got in the first quadrant, and we use it for all other quadrants. So here we go. This is what they're trying to say. If we know that if I went all the way around, all the way to this side, at this point, I'm at 180 degrees. But 180 degrees is equivalent to pi radians. What we can see is that starting from pi radians, if I then said, well, from here, I went backwards by 60 degrees, I would get the exact same triangle, because that's still 60 degrees, 60, they're congruent. They're exactly the same triangle. So up to this point, that's 180. So I start off 0, go all the way around the circle, that's 180. Well, what if I took 180 and took 60 off? I'd be there, right? So that means this side is 120. That's 120, and that's 60 there, right? Now that I've got this triangle, that's 60 degrees. That's 90 right here because that's a right angle triangle. These two are pretty much the same. But what's nice is that if I said, what is the cos, which is the x values of this length, clearly it's still half, but what's the difference? It's negative because the x values are negative on that side. So it's negative half. So when they say, what is cos of pi minus pi on 3, that literally is what I just described. Pi is 180 minus 60 degrees. That's all I did. I started off 180 and I minused 60. That's why I'm in this region. So cos of pi minus pi on 3 is really just quadrant 2. Then you look at this one. Why is it plus? Is because starting at 180, if I added 60 degrees, I'm now in third quadrant. So really, symmetry property is all about you drawing that shape, that same triangle 4 times. It's 60 here, it's 60 this way, and you get those 4 different points. This point here is the result of you doing pi plus pi on 3, or 180 plus 60. The result of this point was you starting off at 360 degrees and then minusing back by 60. So that means it's 2 pi minus pi on 3. So for every question, when you say, what is cos, you're just saying, at that point, what's the x value? at that point, what is the x value? And pictorially, I can already see. Third quadrant, x is still negative. That length is still negative half. So this is half. That's negative half. And then this is half. That's symmetry properties. So your job, no matter which one of these I give you, your job is to figure out where's the starting point. Is it at pi or is it at 2 pi? Because if you know it's 2 pi, you can go up or you can go down. If it's pi, you can go up or you can go down. So the ones I just gave to you before when I said, what's cos of 23 pi on 6? Your goal is to make it a whole number as close as possible. Because if you know it's a whole number, odd numbers on this side, even numbers on that side, then you know where to start. So let's do an example. Let's pick, actually these ones are relatively, let's do this one. Just the bottom corner there. So if you had to answer this in your head, I want you to picture the unit circle in your head. So you got a unit circle. Your first question should be asking, I've got 22 on 3. Where's the closest whole number do I have? Because that's dividing by 3. So you got to think of your 3 times tables. 22 is closest to what in terms of your multiples of 3? Which one do you have? 21 or 24. But out of the two, clearly, it's closer to 21. So how do I get 22, negative 22, to become a 21? Well, the only way was it had to be negative 22 pi, or sorry, started with the negative 21. Negative 21 pi on 3, had I just subtracted an extra pi on 3, that is equivalent to negative 22 pi on 3. Get me? Now, if you see this, let's picture that on your unit circle. You told me it's 21, but 21 divided by 3 is negative 7. Now, negative 7 pi, you can figure out where you are in the unit circle. Positive is this direction. Negative is the clockwise direction. So let's work it out. If you started from 0 here, going all the way here is negative 1 pi. Going all the way here is negative 2 pi. Going all the way back here is negative 3 pi. If you keep following that, all the odd numbers end up here. So that means negative 7 pi. This here is negative 7 pi minus pi and 3. Where's negative 7 pi? It has to be on this point. You're starting here. That's where negative 7 pi must be. Now, all you have to figure out is, if negative was going clockwise and I'm now minusing an extra pi and 3, which region am I going to fall in? I'm going to move further negative. I'm in the second quadrant. That's the skill that you need to have a picture in your head. And that's the most challenge, okay, especially when you work with negative angles. So here, once I know I'm in my second quadrant, I know I had to go from negative 7 pi, that's negative 21 and pi and 3. And I need to minus pi and 3, so that means that angle there's pi and 3. All you're trying to figure out is cos, which means what is the length of cos of pi and 3, which we just did. We just did that. So this is the same thing as saying the negative answer. Remember, cos is going to be negative in this region. So negative of cos of pi on 3. Then you use the exact values. What's cos of pi on 3 again? Half. So the answer must be negative half. So what's the biggest challenge that you can have here? It's literally trying to picture where you are in the unit circle. Okay, if you know where you are in the unit circle, and the radians help. The radians help you to figure out where to start. Even numbers on this side, odd numbers on this side. Then once you know where to start, that's how it works. What are the challenges in year 11? Is the fractions. The better your fractions, the easier it is to do this part. Okay, so that is exercise 6ABC. So what was A? Degrees to radians. Radians to degrees. B? Exact values. C? Symmetry properties. You can't do symmetry properties without knowing the exact values. And then you can't solve, which is 6F, you can't solve for these equations without knowing your symmetry properties. So by the end of next week, I do expect that 1, you're going to learn all your exact values. 2, eventually you'll be able to do these type of questions. I say like tan of 5 pi and 4. You think in your head, I already think that's 4 out of 4 is 1. So I'm at 1 pi, add an extra, so that means I'm in third quadrant. What's the tan? Tan's the gradient. Gradient is positive, so really I'm just doing tan of pi and 4. which is 1. So it must be positive 1. So you have to be able to do that, but quicker. You know, just thinking about it, picture in your head. But you start off by drawing. You start off by drawing, and over time you get better at that. So just find out where you are on the unit circle first, and then you should be able to do it. Okay, so starting from tomorrow, I'm going to be quizzing randomly. I'll just be calling you out. I might just be saying like 10 of, I don't know, 11 pi on 4. And you tell me what that answer is. You know, and I might say cos of, I don't know, 16 pi on 3. Something like that. All right, team, I'm going to pause, stop the video there. That's it for today.